So let us consider this I vector, I cap actually. So I cap here, it is represented as what? That is x vector divided by x. Do you understand? Or x vector divided by x vector modulus. X vector modulus is nothing but the magnitude. So that is why I put simply x. Do you understand? Then similarly, I cap, j cap, what is that? Y vector divided by y. K cap, z vector divided by z. Got this point? Okay, right? So in that case, we can represent that is x vector as that is x into I cap. Do you understand? So x into I cap. Y vector as y into k cap. Z vector can be represented as z into this is j, sorry, j cap, and this is k cap. Got it? Okay. So these are all called orthogonal vectors. And this is called the orthogonal unit vectors. What are those orthogonal unit vectors? I cap, j cap, k cap. Got it? Now, localized vectors. Next one. Localized vectors. Localized vectors. These localized vectors are the vectors whose initial points, that is point is fixed, and that is known as localized vector. The initial point is fixed. Okay. For example, position vector of a particle, that is from the initial point, lies at the origin. For instance, that is if an object is moving on the origin, so it moves like this. It can move like this. It can move like this. It can move like this. So these are all position vectors. Okay. Non-localized means non-localized. Okay. Vectors. These localized vectors, the initial point is not fixed. Here, initial point fixed, whereas in this case, initial point not fixed. So such type of vectors are called non-localized vectors. For example, vector velocity vector of a particle moving along a straight line. It goes somewhere from somewhere to somewhere. Okay. So if you represent like this, it means that it is a not a localized vector. So it can be called non-localized vector along any straight line without indicating any reference point. Okay. Then position and displacement vector. This is very, very important. Take down. Position vector. Okay. So this position vector, a vector that gives position of an object. Take down. A vector that gives position of an object. Okay. With reference to, that is very important. With reference to the origin. With reference to the origin of a coordinate system. Of a coordinate system. What do you mean by coordinate system? This is x, y, z. So from O, you have got A. So this OA is position vector. OB another position vector. OC another position vector. I hope now you should be able to understand. So and that is it can be of any type also. Then this can be indicated, for example, it is not necessary that it will be going in this direction like orthogonal vectors. It can also go like this. It can also go like this. It can also go like this. But they have started only from the origin, right? Now, let me consider OA, a position vector. OA, the position vector. And this OA is represented as R. Okay. Now, this is a two-dimensional part, x-axis, y-axis, right? And a position vector that subtends an angle theta. Okay. So this is O and this is A and this is called R vector or OA vector. Okay. So what do you call it? OA vector or R vector. Okay. That subtends an angle theta to the x-axis. Okay. Now this position vector provides a two information. That is, it tells us the minimum distance of an object from the origin, how much it is traveled, and it tells us about the direction of the object with respect to x-axis, and y-axis. Okay, so we are able to track the vector, and such type of vectors are called position vectors. Now let us move to displacement vectors. Displacement vectors. So here, this vector tells how much and in of which direction the object has changed its position. Okay, so this is known as displacement vector. So it means change of position. Change in position. It describes the change in position in a given interval of time. In a given interval of time. Okay. So such type of vectors are called displacement vectors. For example, let me consider that is the same O, origin. From the origin, you have got the x-axis here and y-axis here. Okay, let me consider a position vector of that is OA. This is the position vector. Okay, so let us call it R1 vector, right? And that is another position vector, and its position is, that is, its vector is R2 vector. Do you understand this? Now, the displacement vector means, for example, let me consider this. This object has moved from here to here. Okay. So that is indicated as what? Displacement vector. Okay. So what do you call it? This is called displacement vector. Displacement vector, and that is represented by delta R vector. Okay, that is represented by delta R vector. It means that is it has taken taken a time t to travel from A to B. Okay, so this A can be represented as x1 by the point x1 comma y1. Do you understand? And what about the point B, that is x2 comma y2? This is point B. Okay, it means what? For example, you can indicate this A by referring to the graph like this. Is that no? So what about this? This is x1 and the relevant point is y1. So you can represent this as x1, y1. You understand? Similarly, now it has traveled to B. So B means here. So this is x2 and the relevant y2. Okay, so that point can be called y x2, y2. Do you understand? Now, how to represent this R vector? So this R1 vector can be represented as, that is, x1 I cap plus y1 j cap. Do you understand this point? Similarly, R2 vector can be represented as x2 I cap plus y2 j cap. Right? Pardon? This this one. Yeah, that is being, yeah, this R1 is represented, this is the representation. R1 is represented as x1 I cap. So this is the point x1 I cap and plus y1 j cap. So we include these two vectors, okay, as a graphical point, and we take this as x1 I cap plus y1 j cap. This is called R1. So this indicates the displacement. I mean, it is not indicating displacement. This indicates the position vector. And similarly, because by why it is called position vector, the x-axis alone will not be sufficient to indicate the position. Do you understand? Right? So in that case, you need a second dimension, that is y. So using this x1 and y1, we can identify, okay, in this graph, it is available here. And that's why we take this as what? R1 with a combination of x1 I1, x1 I cap plus y1 j cap. Similarly, R2, that is x2 I cap plus y2 j cap. Now, the position difference, that is displacement, is the change of position, as I already mentioned, delta R. So, which is nothing but R2 vector minus R1 vector. Okay. So, in that case, now we have to substitute this. So, delta R is equal to what is R2? R2 is x2 I cap plus y2 j cap, close the bracket, and minus, and what about this x1 I cap plus y1 j cap, okay, and now this I cap being common, we can take outside the bracket also. So x2, and this is minus, so x2 minus x1 of I cap plus y2 minus y1 of j cap. Okay, and this can be called as, that is delta. Now we are interested to find out what is this delta R. Okay, so this is delta R. Now we are interested to find out the magnitude of this displacement, because still it is the R vector only. So we are interested to find out the or delta R vector, we are interested in magnitude. So what we are supposed to do, that is we can take the square root of this one, and where we apply the distance formula. In coordinate geometry we used to do. So delta x, that is delta R vector modulus, it means delta R. That is the magnitude. That is nothing but the square root of x2 minus x1 and then whole squared plus y2 minus y1 the whole squared. Okay, x2 minus x1 the whole squared and y2 minus y. You may ask me, sir, what happened to that I vector? That I vector, when it is squared, that is multiplied by its own axis. For instance, I vector dot I vector, it gives 1. J vector dot j vector, that gives 1. K vector dot k vector, that gives 1. Okay. In the case of scalar product, and at that time I will be explaining about this. Anyway, since it is required, I am sorting out this. Okay. Now, mm, okay, so we have completed that delta R, which is nothing but what? Delta R vector modulus, which is nothing but delta R, that is square root of x2 minus x1 the whole square plus y2 minus y1 the whole square. Okay, right. What is your question? Co-initial vector. It is not co-initial vector. You mean that null vector or the position vector? Which one you refer? Position vector. Yes, it is apparently, but we give a distinct name for them. Co-initial vector means that is that doesn't represent the position exactly, but in this case it is starting from the origin, so it is something specific. That is more generic. Okay, right. Next one. The Now I was explaining about the displacement vector. So this displacement vector is given by this formula. Okay, got this point? And this is the magnitude, and this one is the vectorial representation. Don't forget this. And this is the magnitude because we have taken the square. So taking square of this one, that is eliminated. Okay, because we know I squared means I cap squared, that gives you always 1. So I have removed this 1. Then the magnitude of displacement is either less or equal to the path length of an object between the 2 points. Similarly, you can represent the three-dimensional aspect also. For three-dimension, you have to consider the z-axis also. So z2 minus z1 of what? There you will get what? K. Is it not? K cap. So shall we try to put the that is displacement for that? So how it can be? For instance, listen to me. Let me explain about the z vector. I mean three-dimensional vector. This is x-axis, that we call it y-axis and z-axis. Okay. Now, when it was x and y, two-dimensionally we were able to explain. But when there are spatial points involving all these three coordinates, for example, it can be above the plane of the paper like this. Another object is below the plane of the paper. So in that case, how to represent that? This y is above the plane of the paper. Okay, so that is, say, let me say that is 5 centimeter above the plane of the paper. And that is, it is located here. So 3 centimeter away from the origin, and it is located here 2 centimeter away from the origin in the z direction. Now we have got this point. Okay, so let me assume that I am having one point here involving x1, y1, z1, right? So that involves all the 3 points in order to indicate the position. Do you understand? Right. Now three dimension means space. So spatially, how they are like a mosquito flying in the hall, where it is, that is point, and that point is represented by x1, y1, z1. Similarly, you've got another point here, that is x2, y2, z2. Okay, and this point can be, for example, let me put the same A and B. So what is the position vector? This is OA is the position vector. What about this? OB is the another position vector. So let me represent this as R1 vector. And what about this as R2 vector? Now this mosquito is flying to that position. So it means in this way. Okay. So it means that is we are interested to find out this delta R vector initially. So how to represent this one? So we have to involve all the three vectors like delta R vector. And before that, you must put what is R1 vector. So the R1 vector is nothing but the what? The composition of this x1 I vector plus y1 j cap plus z1 k cap. Do you understand? And what about the r2 vector? So here you have to put x2 I cap plus y2 j cap plus z2 k cap. Do you understand? Now we are interested in R2 minus R1. So delta R cap is R2 minus R1. So this can be represented as X2, and the relevant that is I can be subtracted. X2 minus X1 of I, right? And similarly Y2 minus Y1 of J cap. And similarly Z2 minus Z1 of k cap. Do you understand? Now let us further make it as a, so this is the vectorial representation of the displacement as far as 3D is concerned. Okay, so in that case, now let us take the delta R vector models. Then you have to take the square root of this one. So take sum of squares of all these vectors. So we can put that is square root of x2 minus x1 I means that becomes square. So it is 1 plus y2 minus y1 the whole square plus z2 minus z1 the whole square. Okay, so we are eliminated completely what these I and because I dot I, j dot j, k dot k is equal to 1. Are you able to follow? Okay, right. Then actually we are taking the whole square or able to understand the whole square root of root 2. So it means the other part that is I dot j will become 0 and that is why the other terms are completely eliminated because they will become 0. When you got I into j, it becomes 0. So the entire term is 0. J into k is 0. The entire term becomes 0. K into j I, that becomes 0. The entire term is 0. And that is why we are taken, for example, you may struck with this point. For example, sir, when you put a plus b the whole squared, what do you mean by this? You will put a squared plus b squared plus 2ab. Okay. And but in this case of this xi, that is, I put this x1i, x1i cap plus y1j cap. I will not at all consider this 2ab. Can you explain? One thing I have given clearly that is I dot I is equal to 1 and that is why I am getting only that relevant x squared, y squared, etc. But in the case of 2ab, it's how I have eliminated. Means basically 22 to yeah, that is when this A is yeah. So your 2ab means you will put so 2 in 2ab means 2 into you will put x1 I cap into y1 j cap. Okay, j cap. We already know I cap dot j cap that becomes a 0. So this whole term becomes a 0 and that is why we are totally eliminated and we are taken only a squared plus b squared. In the case of that is x squared plus y squared. In the case of this one that is I made the difference as difference. Okay, clear? Right. And then so this is very important. So this is with regard to 3D, okay? But we are not going to study this 3D. We are going to stop with this 2D only. Just for your academic interest, I extended this one also, okay? So if there is any doubt, you can ask me.